Hi, I'm Reza Kudusian, and I'm going to present you the work ACE. It's a fine-tuning mechanism for visual language models to improve their video understanding. So this work is focused on procedural videos where a sequence of fine-grained actions take place to carry out a high-level action. It's very important for human-machine interacting systems and detecting and recognizing anomalies. Now, what are anomalies in such cases? There are missteps, redundant steps, or sometimes deviations from expected sequence of actions. Lastly, unseen actions are the last example of anomalies. We focus on unseen actions for this work. Now, why does classifying unseen actions matter in procedural videos? Sometimes we're not able to collect classes, all potential classes for action understanding. For example, cutting finger or spilling hot water. Such classes are very hard to acquire. I don't think any of you want to go through that process. Sometimes we can't really practically cover all sorts of classes, so we can only train for certain classes. Hence, there are classes that are unseen at test time when we need to still classify them. Now, just a brief introduction of what vision language models are. They consist of encoders, one encoder for videos and one encoder for text. The goal is to bring close together the embeddings in a joint embedding space for any corresponding pair of text and video. Now, I'll ask you to put you through a human study. In this human study, you can see a video of someone performing such an action on 4 classes of action being described by 4 different verbs. You can pause the video and do the test yourself and pick the best fitting description, in this case mix. Next example, same video being played. Now we have new permutations of the same action described by different labels. Dissolve. Now lastly, again, same video, 4 new sets of descriptions. Which one's a better fit? Stare. So as you saw, mostly humans are very well doing. Humans do very well when it comes to recognizing actions, regardless of how they are described or what action synonym is being used to describe the actions. We call this synonym robustness test. The issue is our models are not as sophisticated and as equipped as humans when it comes to recognizing actions when they're described with different labels and synonyms. The goal is to apply ACE so that the model becomes more robust regardless in classifying the action regardless of what action synonym is being used to describe them. The problem we do is that we train a model based on a set of seen actions. We call them base actions too, and then test them on unseen and seen actions separately. So there are 2 different scenarios, seen actions and unseen actions. We also call unseen actions as novel classes of actions. Our method is very simple and easy to integrate for the vision language models, which we hope will be applicable to you. So let's delve a little bit deeper into the methodology. We have a fixed loss function, which is normal classification loss of vision language models, where we increase the probability of the correct label giving its corresponding video. In the presence of other labels, you can see you have stare, fold, shake, spread, and their embeddings. It's fixed because the labels, there are default labels provided by the dataset. Now, we want to make sure the model is robust to the choice of action synonyms. Hence, what we do is that we substitute those labels with their synonyms randomly. For example, stare has multiple synonyms that are automatically generated by an LLM, for example, GPT-4. They could be mixed, dissolve, or stare. We replace them randomly. At every iteration, a synonym is randomly chosen for each class. Here you can see for the classes of spread and stare. So in iteration 1, you have the following: stare, tuck, rock, smear. And the next one, you have whip, tuck, shake, lather. These are just random permutations of the same classes being presented by different synonyms. Hence, we call this loss function the random loss function because it provides us with the capability of finding the right class when such permutations are unseen during training too. We simulate the test time, because in test time for unseen classes we have unseen permutations of classes. Now we have the same classes, but we use unseen representations of them, so the model becomes robust to unseen, I guess, unseen text representations, and it doesn't overfit to fixed labels. However, this comes with the limitation that the model might get biased to the object, because sometimes learning the object might allow the model to recognize the correct action. So what we do is that we augment the classes with one additional negative label that's randomly chosen and that label is composed of the same noun as the correct label and a wrong verb. In this case, mixed t is the ground truth label, hence we use t as the noun, and a wrong label randomly chosen as jitter. So when the model gets biased to recognizing the action label of mixed t by only focusing on t, we confuse it by introducing jitter t. So now it has to pick between jitter t and mixed t, which makes it focus on the verb, and focusing on the verb allows it to debias the model from overfitting to the object. Lastly, whenever it comes to finding the similarity between a text description and a video, we simply average the pairwise similarities between all synonyms of the label and the video. This helps to augment the text and then also describe unfamiliar verbs with more familiar synonyms. We call this leaf augmentation. Now quickly we go over some of the results. We can see an abolition study of different components. As you can see, we show mean and standard deviation of testing over 10 different permutations of action synonyms for the unseen classes instead of using fixed labels. And this is a more comprehensive table comparing with the state-of-the-art vision language models. You can see for seen classes using default labels, unseen classes using default labels, their harmonic mean, and the SRT, which is the synonym robustness test, run over 10 permutations of randomly chosen action synonyms for the unseen classes. And our model produces the highest mean in most cases and the smallest and a very small standard deviation. We tested on 3 different datasets: GTEA, ATEA, GTEA, ATA, and IKEA. We showed that the quality of our model depends on the quality of the synonyms. We changed the GPT-generated synonyms with manually chosen synonyms for the GTEA dataset, and we show results improve. We also show that obviously the quantity of those synonyms matter to a degree, but eventually the quality goes hand in hand with the quantity. And finally, you can see the text representations in the embedding space. We see the text embeddings of the synonyms of each class being represented by planets in the galaxy of the action concept space. Ideally, you want all the planets or all the synonyms to be close to each other and far from the other galaxies. And each galaxy is a metaphor for each action concept space. And as you can see, the top half is the clip model before applying ACE, and the bottom half is a clip model after applying ACE, where the galaxies are placed more intuitively to other galaxies that are more relevant to each other or irrelevant to each other. They're further apart and their synonyms are closer and more disjoint from the synonyms of the other actions. Thank you for listening.